Welcome to your geometry week of February 2nd. Welcome to February. So we are starting a brand new unit in geometry this week. We're going to start unit 6. So at this time, I do want to make sure that you have your math notebook out. Remember, it is required that you are taking notes, and the reason is it's going to make the lessons and graded assignments a whole lot easier when you take notes during this recording. Then when you go through the lessons this week, you'll already have some exposure to those concepts, and then those lessons should just reinforce those concepts. So in your math notebook, I want you to complete a probability question. So I know you've seen some probability in some of your other math classes before. And let's see if we can remember how to find some probability with just a warm-up question. So in your math notebook, I want you to complete this. The question is, or the situation that we're starting with is that we have 10 marbles in a bag. There's 2 red, 3 green, 3 orange, and 2 purple marbles. So I want you to find the probability of choosing a green marble, and then you put that marble back that you chose, and now what is the probability of choosing a red or purple marble? So go ahead and take some time and solve these, see if you can remember how to solve these types of problems, and then when you're ready to click or ready to check your work with mine, go ahead and click play. So you can pause these recordings so that you can take notes and try some problems on your own. All right, so remember, to find the probability of anything, we want to first, on our numerator, the probability of finding a certain event, you want to find the number that goes on top on the numerator is the number of the ways an event can occur out of the total number of possible outcomes. So if we want to find the probability of choosing a green marble, we have to think, well, how many chances do we have of choosing a green marble? Well, there's 3 green marbles, so we have 3 different ways that we can choose one green marble. And then the probability of all outcomes. So we want to add up or figure out the total number of marbles that we're choosing from, and we were told that we have 10 marbles. So the probability of choosing a green marble would be 3 over 10. We can also write probabilities as a decimal, so if we just take 3 and divide it by 10, that would be 0.3 as a decimal. And then, of course, if we wanted to change that into percentage, you move that decimal 2 places to the right and you would get 30%. So there's actually 3 different ways we can write probabilities. You can write as a fraction, a decimal, or a percentage. So now we put the marbles back, or that green marble or the marble that we chose, we put it back, so we're still at 10 marbles total that we can choose from. Now we want to find the probability of choosing a red or purple marble. So do you remember what we do when we see that word or when we're working with probability? We add the 2 different probabilities. So what we want to do is first find the probability of choosing a red marble, and then add that to the probability of choosing a purple marble. So I've just written a little different notation here. I put a capital P in parentheses in red, in parentheses. That means, what is the probability of choosing a red marble? That's what that means when I have the capital P and then I have parentheses and some stuff in the parentheses. That means probability of choosing a red marble. Same thing over here, capital P, parentheses, and in the parentheses it says purple. So that notation means the probability of choosing a purple marble. So this is how we're going to tackle this problem. First, we're going to find the probability of just reaching in and grabbing a red marble. So what would that probability be? Well, we have how many red marbles in that bag? We have 2 red. And there's a total of 10. So the probability of just choosing a red marble would be 2 out of 10. We're going to do the same thing for purple. What's the probability of choosing a purple? Well, there's 2 purple marbles, so 2 out of 10. And then, because of that or, we're going to add these two together. We're going to add these two probabilities together. So just a quick review, when we add fractions, we have to have the same denominator, and we do. So we can go ahead and just leave the denominator as 10, and then you add the numerators together. So 4 out of 10 would be our answer. Again, if we wanted, we could go ahead and put that in a decimal. If it asked for it, the answer in decimal form, we would say 4 divided by 10 is 0.4, and that is also 40%. So again, probabilities, we can express our answers in fractions, decimals, or percentages. So we talked about probability in our warm-up and what it means, and how we can also write a probability in notation form with a capital P on the outside, and then whatever event that we're trying to find the probability on the inside. So here, let's I think we've done a great review of just finding simple probabilities. So we've got a picture below of some puppies. What would be the probability if we were to pick a yellow lab from this bunch of puppies below? So again, the number on the top is the number of ways the event can occur. And here, if we wanted to write it fancy, we could say the probability of choosing a yellow lab. What would be that probability? The number of ways that we can choose a yellow lab, well, there's 1, 2, 3, 4 yellow labs to choose from. And then what is the total number of outcomes? Well, there's 1, 2, 3, 4, 5 puppies to choose from. So that would be the total number that we could choose from is 5. So the probability of choosing a yellow lab would be 4 over 5. Alrighty, so in Unit 6, you're going to start learning about theoretical or experimental probability. And what is the difference between experimental and theoretical probability? So theoretical probability is what we expect to happen. What we expect to happen. An example of theoretical probability is if I were to say, what is the probability of when you flip a coin of getting heads or tail? And we would say 1/2, because theoretically we know there's a 1/2 probability. Where experimental is when what actually happens when we try it. What actually happens when we try, a situation out. So let's look at some examples and classify them as theoretical or experimental. So if we toss a fair coin up, what is the probability that a tail will show up? Do we know what that probability is? Can we expect a certain thing to happen? We can. So we would say in this case is theoretical. We would expect it would be a 1/2 chance. I kind of talked about that one before. It would be theoretical because we can expect it would be a 1/2 chance. So a bag contains, let's look at the next example. A bag contains 20 marbles, 15 of them are red and 5 of them are blue. Find the probability of picking a red marble. Well, we could find the probability by using the probability formula, and that would tell us what we can expect to happen. So again, this is an example of theoretical, using our using the formula of probability to figure this probability out. So we're using what we can expect to happen. It would be theoretical. So here, let's say that we use a simulation tool to find the probability of rolling a 3 on a dice. Or let's just say we take a dice and actually roll the dice 50 times to collect data. So we're actually taking a dice and rolling it to collect data. Because we're collecting data and actually doing it, that's experimental because we're actually trying it and collecting our data. So in here would be experimental. And you'll have a chance to practice with that this week of classifying as theoretical or experimental. Alrighty, so let's keep going with this idea of theoretical and experimental probability. So we've got an aquarium that we've stocked with a bunch of different fish. We've got 25 neon tetrafish, 18 swordtails, we've got 12 platies, and 3 catfish. So we're going to just use N to represent neon tetras, S to represent swordtails, P platies, and C to represent catfish. So a geometry class is on a field trip at the aquarium and is recording the numbers of fish observed in the aquarium. During a 15-minute period, the class observed 18 neotetras, 10 swordtails, 9 platies, and 2 catfish. So let's start with finding the experimental probability of observing a neon tetra. We want to find the experimental probability. So which data are we going to use to find the experimental probability? Would we use this data here? Or do we use the data that tells us exactly how many fish are in that aquarium? Well, because it's asking for the experimental data, or the experimental probability, we want to use this data here, the what the class observed and wrote down. So we're going to use this data here. So what's the experimental probability of finding a neon tetra? How many neon tetra did they see? 18. So we saw 18 neon tetra over what's the total number of fish that the class observed? Well, let's add them all up. 18 plus that 10 swordtails, the 9 platies, and the 2 catfish. So when you add all those up, I got a total of 39. I added up 18 plus 10 plus 9 plus those 2, and I got a total of 39. So the experimental probability would be 18 over 39. We can write that, if we want, as a decimal, which would be 0.4. I always round to 2 decimal places, 0.46. Now let's find the theoretical probability of observing a neon tetra. So now we're going to go theoretically, we want to use the total number of fish in that aquarium. So we're going to go up to this data. Neon tetra, there are 25. So 25, how many total fish are in there? Well, 18 plus 25 plus 12 plus 3, 25 plus 18 plus 12 plus 3. There are 58. So if we want to find a decimal form, 25 divided by 58 is 0.43. All right, so that's just an example of using experimental data that we've gathered versus theoretical, which is using all the data that we know is there. I'm going to go to the next slide now. Dependent versus independent is 2 different types of probability. Dependent is when one event affects the other. Dependent, just like when you're dependent on somebody. When you're dependent on somebody, the actions of that person you're dependent on is going to affect you. So an event that is dependent is where one event affects the other. An example would be like picking a card from a card deck and then not putting it back. So think of that, because there's 52 cards in the deck. So originally we would have a total of 52 cards to choose from, but if we don't put a card back, now we would only have 51 cards to choose from. So that first event of not putting it back is going to affect the number of outcomes in the second event. So that's an example of a dependent event. Where an independent event, somebody who's independent is able to do things, get things accomplished on their own. So one event is going to have no impact or influence on the other. For example, if you needed to find the probability of rolling a certain number on a dice and picking a card from a deck of cards, well, the dice and the deck of cards have nothing in common. They're 2 different objects. So these 2 probabilities are going to be separate from one another. They won't affect one another, so they would be independent. I'm going to go on to the next slide. So two events are said to be independent if the result of the second event is not affected by the result of the first. If A and B are independent events, the probability of both events occurring is the product of the individual events. So how do we find the probability of independent events? Right here. So if we're trying to find the probability of event A and B, and they're independent, we're just going to multiply the probabilities of each event occurring. So let's take a look at what I mean here. It really goes back to that original warm-up problem we did, where it was an example of an independent event. So let's look at another one though. So a drawer contains 3 red paper clips, 4 green paper clips, and 5 blue paper clips. We're going to take one, we're going to reach our hand in and grab one paper clip and then replace it. And then we're going to reach in and grab another paper clip. So the important key word is that when we chose after we chose that first paper clip, we put it back. So now we want to find the probability that the first paper clip is red and the second paper clip is blue. So we're going to reach our hand in twice. We're going to grab the first paper clip, and then we're going to grab another one after we put the first one back. We want to find the probability that we reach in and we grab a red one, and then we reach in and grab a blue one. So let's figure that out. Because we replaced the first paper clip we chose, that means that our second event of choosing that blue paper clip is not going to be affected by that first reach in and grabbing the paper clip. So what we want to do to figure out the overall probability is find the probability of reaching in and grabbing a red paper clip. Then we're going to multiply that times the probability of reaching in and grabbing a blue paper clip. So we're going to treat these one at a time and then multiply them together. So the probability of choosing a red paper clip, how many red ones are there? There were 3. There were 3 red paper clips. How many total paper clips? 3 plus 4 plus 5. 3 plus 4 plus 5. So there's 12 paper clips. So that would be our denominator. And we're going to multiply that times the probability of reaching and choosing a blue one. How many blue ones are there? There are 5. There's still a total of 12 to choose from because we replaced our first choice. Now let's do the multiplication. 3 times 5 on our numerator is 15. 12 times 12 is 144. We can reduce that. 15 divided by 144. Let's see, we can divide our numerator and our denominator, it looks like by a 3 if we want to simplify that. You can leave it as it is. We can also write it as a decimal. 15 divided by 144, around to 2 decimal places would be 0.10. So that would be our probability of reaching in and grabbing a blue one and reaching in and grabbing a red one with replacing our first choice. Independent event. So that is how we find the probability of independent events. We find the probability of each one separately and then multiply them times each other. I'm going to move on. Dependent events. Dependent. Remember, dependent is when the second outcome is affected by the first event. So now our formula to figure this out is a little bit different. So what we're going to do is we're going to find the probability of just that first event times the probability of that second event once A has occurred. And that's what that means when you have B and then that line A. That means B once A has occurred. So just so you understand what the notation is, and you're going to see that this week, when you've got B and then that line there and A, that means the probability of event B once event A has occurred. So let's look at an example, and it's going to make more sense. We're going to have the same situation here, that drawer full of paper clips that we're going to reach in and grab some paper clips, but we're going to choose one paper clip and then we're not going to put it back. We're not going to put that paper clip back. We're going to hold on to it and then we're going to reach in again and grab another paper clip. So we want to find the probability that the first paperclip is red and the second paperclip is blue. So the probability of how we figure that out is we're going to find the probability of choosing the blue, or I'm sorry, red. Red was our first one. Red. Oh, that's. And then multiply it times the probability of choosing a blue one. BLUE. Once the paperclip, remember, is not replaced. So the probability of finding a red one, we already know, is 3 out of 12 times the probability of choosing a blue one. Well, how many blue paper clips are there? There are 5, but now what's different is our denominator. Remember, we're holding on to that first paper clip that we chose. We're not putting it back. So now we only have 11 paper clips we're choosing from when we go to find the blue, probability of the blue. That's the big difference there, is now that we're holding on to the first paper clip we've chosen, it's going to affect the total number of paper clips we have to choose from. Now we only have 11. So now our probability 3 times 5 on our numerator is 15. 11 times 12 is 132. So I've got a little bit of a probability difference here because of that difference in the total number of paper clips. So if we were to find the decimal format, 15 divided by 132, we would get 0.11. I'm going to go on to the next slide now. So just remember that with dependent events, the dependent events are affected by the previous events, such as removing marbles from a bag and not putting it back, where independent events, such as tossing a coin and maybe rolling a dice, they're not affected by one another. All right, so let's keep moving here. Session 2. So I really want to go over this question just because this is actually a question from your homework in Session 2. In Unit 6, Session 2, this is pulled right from one of your homework problems. I typically get a lot of questions on this question from this Unit 6, Session 2 assignment, so I just thought we'd go over it in this recording. So when you get to this question, you should have the work already in your math notebook and ready to put down in the assignment. So here we've got a table showing immigration to the United States from 3 different countries in 3 different years. So immigration, people coming to the United States, we're keeping track of where they're coming from and keeping track for the year 1990, 1995, and the year 2000. And we want to find each probability. The first probability we want to find, that a selected person is from Cuba, given that the person immigrated in 1990. So we're trying to find the probability that a selected person is from Cuba, given that that person selected immigrated in 1990. So what we want to do is, it says they immigrated given that they immigrated in 1990. So we want to focus on the 1990 column because it says given that the person immigrated in 1990. We want to focus on that column. So what we want to do is they're asking, we're focusing on the Cuban immigrants. So we're going to focus on this number right here. And then given that they immigrated in 1990. So we want to, on our denominator for part A, it's going to be the number of people that immigrated in 1990 that were from Cuba. So we're going to use that number, the 10,000, oops, that's my 10,645. And then, what's the total number of people that immigrated in 1990? That's going to be our denominator. So we need to add all the people who immigrated to the United States in 1990. So we're going to add 10,664 plus 4,466 plus 1,886. So we're going to add all these numbers together to give us the total number of people that immigrated in 1990, and that would be our total number of outcomes that would go in our denominator. So go ahead and grab your calculators and start adding those together. 10,645 plus 4,466 plus 1,886. Grab your calculator, add those all up. I got a total here of 16,997. So let's go ahead and put that on our denominator, and that is the probability that we're looking for. I think it says, no, it doesn't say about anything. We can leave our answer like that, or we can put it in a decimal format. 10,645 divided by that 16,997. When I divide those two numbers, I always like to round to 2 decimal places. Oops. I want to round up since that number behind the 2 is a 6, so it would actually be 0.63 or 63%. All right, so look at part B. We're done with part A. Let's look at part B. It says the probability that a person came from Spain and immigrated in 2000. So we want to find the probability that they came from Spain and immigrated in 2000. So let's go ahead and erase that stuff in the chart so we can focus on our new question. Came from Spain and immigrated in 2000. So we're talking about that number of people that came in 2000 and were from Spain. So 1,264 people immigrated from Spain in the year 2000. So that is going to be our numerator. And now our denominator is the total number of people who immigrated to the United States overall, not in any specific year. That's going to be our outcome, is the total number of people who immigrated here. We got to add a lot of numbers together, don't we? So what I would do is go ahead and add your columns together. So add each column together, get your total. We know the first column is 16,997. We already did that one. Go ahead now and add the column for 1995. Let's add those numbers together. And then we're going to add all of our column totals together. So 17,937 plus 3,152 plus 1,321. I got a grand total of 22,410. Then we're going to add the last column together, 20,831 plus 4,344 plus 1,264. And I got a grand total of 26,439. Add all those column totals together now. So go ahead and use your calculator, add all those column totals together. Like I said, we were adding a lot here to figure out how the total number of people who immigrated to the United States in those 3 years. And I got 65,846. Let's check that. I'm missing something. Hold on a sec. What am I missing? And never mind, that is correct. We got the correct total there. So we want to put that on our denominator, 65,846. We want that answer as a decimal, so let's go ahead and divide the numerator by the denominator. And we get, go ahead and do that on your calculator. Check your work with mine. I always go 2 decimal places. So I'm going to get 0.2 when I round to 2 decimal places. Part C, the last part we're going to do, we want to find the probability that a person selected, that a selected person immigrated in 1995, given that the person is from Ghana. So there we want to focus on the fact that it says, given the person is from Ghana. So that means that we want to focus on that Ghana roll of people from Ghana. So I'm going to focus on this row here. And it needs to be, the person needs to be from 1995. So that's going to be our numerator right here, where we have the number of people from Ghana in 1995 would be 3,152. So that's going to be our numerator, 3,152. Then again, because it says given the person's from Ghana, we want to find the total number of people that immigrated from Ghana. So add all those numbers up in the Ghana row. So 4,466 plus 3,152 plus 4,000. So when we add this row together, in our calculator we get 11,962. So this are the total number of immigrants from Ghana. So remember it said given that the person was from Ghana. So that's going to go on our denominator. 11,962. We want our answer as a decimal, so we plug that in our calculator to divide our numerator by our denominator. And we want to round to the nearest hundredths place, so that's going to be 2 decimal places. Whoops, that's not a 0. When we plug that in, we get 0.26. 0.26. So again, remember that this is from Unit 5, Session 2, the assignment. This is a question in that assignment. So if you took good notes, you will have all the answers for that question. And you'll know the question when you get to it. All right, continuing on, make sure you do take notes here. If you need more time, go ahead and click pause. I am going to the next slide, where we want to talk about compound events and the difference between mutually exclusive and inclusive events. So a compound event is something that's made up, it's an event made up of 2 or more simple events. So a mutually exclusive event, mutually exclusive, are events that cannot occur at the same time. Mutually exclusive cannot occur at the same time. For example, tossing heads and tossing tails. If we were to toss one coin, we can't have in a result of heads and tails. It's got to be one or the other. So tossing a coin is a mutually exclusive event of getting heads and tail. They can't occur at the same time. If you are turning right and turning left at the same time, that's impossible. So turning left or turning right is mutually exclusive. And the formula, if you will call it a formula, to find the probability of a mutually exclusive event is right here. So finding a event A or B occurring, you first take the probability of event A and add it to the probability of event B. And remember, mutually exclusive is when things cannot occur at the same time. We use that formula. Inclusive events. Inclusive are events that can occur at the same time. Can occur at the same time. For example, turning left and scratching your head. You can do both of those at the same time, so that would be considered an inclusive event. Rolling a 6 and rolling an even number on a number cube are inclusive events because number 6 is an even number, so you can have both those happen. You can roll a 6 and an even number because 6 is even. Because mutually exclusive events can happen at the same time, you don't want to double count for any probability when the event overlaps. So you don't want to double count. We don't want to double count when the events elapse. So that means our formula to find the probability of event A or B happening when they are inclusive events is first we're going to do the same thing that we did with mutually exclusive events, where we will add the probability of event A occurring with the probability of event B occurring, but then we're going to subtract where they overlap. We're going to subtract the overlapping where both A and B occur at the same time. So let's look at some event examples here. So first of all, we've got a card is drawn randomly from 9 cards labeled 1 through 9. So we've got 9 cards and they're labeled 1 through 9. What is the probability of choosing an odd number or a number less than 3? So first, let's decide what kind of type of probability. Is this mutually exclusive or inclusive? So again, we want to find the probability of choosing an odd number or a number less than 3. So first decide, can these occur at the same time or can they not occur at the same time? So probability of choosing an odd number and a number less than 3. Can both those occur at the same time? So ask yourself, can those occur at the same time? They can occur at the same time because in numbers less than 3, so let's think about that. If we have our cards 1, 2, 3, 4, 5, 6, 7, 8, 9, because we've got numbers 1 through 9 labeled out here. And anything less than 3 is going to include these two numbers because it's less than 3, so it can't include 3, so it's got to be 1 or 2, and 1 is an odd number. So they can occur at the same time, which means it's an inclusive event. It's an inclusive event. So remember, the probability, in order to do that, is we want to first find the probability of the first event, which is the probability of choosing an odd number. So let's find the probability of choosing an odd number. And then we're going to add to it the probability of getting a number less than 3. Then we want to subtract out where they overlap. So any odd numbers that are also odd and less than 3. All right, so now we've got our little formula or statement written out. So let's find the probabilities. What's the probability of choosing an odd number? How many odd numbers? We've got 1, 2, 3, 4, 5 odd numbers out of a total of 9. So we would say the probability of choosing an odd number on those cards labeled 1 through 9, there's 5 odd numbers out of those 9 to choose from, plus anything less than 3. Remember, it cannot include 3. So anything less than 3, and I'm going to circle this with green highlighter. So anything less than 3 is going to be these two numbers. So that means there's 2 out of 9. 2 out of 9. And then we're going to subtract out any odd numbers that are less than 3. Any odd numbers that are less than 3, let's highlight that. We'll change the color again to red. I'm going to highlight in red. So any number that is less than 3 and odd, there's only 1, the number 1. So we'd subtract 1 out of over 9. So go ahead, we'll add those two numbers. I'm going to move this over, this fraction, so that we can kind of see those together. Let's add first. 5 plus 2 is 7, 7/9. Then we're going to subtract that 1/9 from there, and 7 minus 1 is 6/9. 6/9. So we've got a 6/9 probability. If we want to put it into a decimal, we would just take 6 divided by 9, and I get 0.67. So that's an example of how we use that formula for an inclusive event where they can occur at the same time. So make sure you take down this example. I'm going to go to the next slide now. A card is drawn randomly, same situation here, 1 through 9 labeled cards. Now, what is the probability of choosing the card 1 or a number greater than 7 or equal to 7? Can those occur at the same time? 1, 2. Can we have a 1 and at the same time as a number greater than or equal to 7? We cannot. So this is an example of a mutually exclusive event. Mutually exclusive. So remember that formula is we need to find the probability of the first event, choosing the card 1, or the probability, so we're going to add a number greater than or equal to 7. And that's all we have to do here. So the probability of choosing 1 is 1 out of 9. The probability of choosing a number greater than or equal to 7, so we've got 7, 8, or 9 that would fall into that category. So there's 3 options out of the 9. Add those together, 4 out of 9. That's done. So that is mutually exclusive. Mutually exclusive examples. And we're going to stop there. So take down all this on your notes. If you need more time, click pause. And that's all. So remember, this is the week of February 2nd key phrase assignment. And I want you to tell me the difference between a mutually exclusive and mutually inclusive events. And that's it. So make sure you complete the key phrase assignment so you get credit for watching this. And let me know if you have any questions throughout the week. Have a wonderful rest of your week.